morning. Welcome to the class of optical communication. Today we'll discuss the topic that is the threshold condition for the laser oscillation and the laser diode rate equation. My name is Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGEC Ghaziabad. So first of all, we'll discuss about the threshold condition for the laser oscillation. Now, if I say, if I know the structure of the oscillation laser, in which you will see that laser oscillations will produce it is a cavity, and in cavity, at one side of the cavity there is a fully reflective mirror, and in another part there is a partially reflective mirror. And in the laser oscillation, in the laser, both spontaneous emission and mainly stimulated emission will take place. When there is a stimulated emission will take place, there is a generation of the photons, and these photons which is generated in the cavity is get out of the cavity from the partially reflective mirror when the energy of the photons is greater than the energy lost by the photons. Means if I say these are the number, let's say these are the number of photons which are generated inside the cavity or inside the laser device. These photons, some photons will move towards the fully reflective mirror, some photons will move towards this mirror. So when the photons will move towards this mirror, and this mirror is a fully reflective mirror, means these photons will get reflected back towards this one, and these photons already in this direction. When the energy of the photons means when the whole energy of the gain of the photons overcomes the losses by the photons, losses in the photons, then then these photons will get pass out from the partially reflective mirror, and output will be from this side. Clear? So this is the threshold condition. What is the threshold condition? That defines minimum threshold condition which is required for the laser oscillation, and that threshold condition is that when the gain overcomes the loss, then only the laser oscillations will take place. Means the photons will get out from the cavity. Now see, steady state oscillations for the laser oscillations are achieved when the gain in the amplifying medium exactly balances the total losses. When the gain in the amplifying medium exactly balances the total losses, that condition is the steady state condition for the laser oscillation. And a minimum threshold gain must be there, must be attained, means must be achieved, so that the laser oscillations can be initiated and they can be sustained. This threshold condition is determined by the change in the energy of a light beam as it passes through the amplifying medium. Now see, when the gain overcomes the losses, or when the gain balances the losses. Now see, what are the losses which is included in the loss of energy by the photons? Let's say if I say the amplifying medium, if I say this is the amplifying medium or the cavity, let's say one mirror have a reflectivity R1 and another mirror has a reflectivity R2. Clear? If I say this is reflectivity R, that is 100%, means this is a opaque, means no photon can be pass out from this one, and all photons which is incident on this will get reflected by this mirror. Clear? And let's say the length of the cavity or the length of the amplifying medium is L. So the amplifying medium, let's say the amplifying medium length having L, completely filling the region between the two mirrors which is having a reflectivity R1 and the R2. On each round trip, beam passes through the medium twice. Let's say, if I say the maximum gain will be what? When the photon is generated here, and this photon will move towards this mirror and get reflected by this mirror and pass on to the another mirror. So that is the maximum gain which is achieved by the photon when it travels through the maximum distance. And the fractional loss in occurred by the light beam will also be the losses. कौन से होंगे? Loss, that is the energy absorbed by the energy which is absorbed by the this reflective mirrors. Clear? And some of the photons get also losses in the amplifying medium. So that is also the loss. So it also provides the, when the photon moves towards this direction, gets reflected by this mirror towards this direction. So it provides a positive feedback of the photon by the reflection at the mirror at either end of the cavity. So optical photon is fed back many times while receiving the amplification, and this structure is known as the Fabry-Perot resonator. Now if I say photon which is produces here get reflected by this fully reflective mirror, let's say, and it moves towards this one, the gain of the photon gets in, but let's say if still the gain is not up to the mark which can pass beyond the fully reflective mirror, then this photon will also get reflected by this one, and this will also achieve. Now if I say this photon has a gain which can overcome the optical loss by the reflective mirror, then that photon will get out from the device. So this type of structure is known as the Fabry-Perot resonator. Now if I say the fraction loss, first of all we will talk about the loss. The fraction loss will be equal to what? R1 into my R2 x e की power minus 2 into my alpha L, that is equal to R1 into my R2 e की power minus 2 into my alpha L. This L is the length of the cavity, length of the amplifying medium, alpha is the attenuation. Clear? Now fractional gain, this gain is what? This fractional gain is due to the stimulated emission, mainly due to the stimulated, that is equal to e की power में 2 into में g into में L, and g is the gain, L is the length of the amplifying medium. Now if I say for the steady state laser oscillation, steady state laser oscillation means the laser oscillation can be initiated and will get sustained. Steady state oscillation will be when minimum, when threshold, when the losses balances the gain. It means that the fraction loss, that is e की power में minus 2 alpha L into में R1 into में R2 multiply में gain, that is e की power में 2 into में g into में L is equal to 1. It means you will see that the R1 into में R2 will be equal to e की power में 2 into में G माइनस में अल्फा इंटू में L इक्वल टू 1. Now for the minimum threshold condition, this G can be written as R1 इंटू में R2 e की पावर में 2 इंटू में G इंटू में थ्रेशोल्ड गेन माइनस में अल्फा इंटू में L इक्वल टू 1. On solving this one, you will see that 2 इंटू में G इंटू में TH माइनस में अल्फा इंटू में L इक्वल टू 1 अपॉन में R1 R2, and you will see that 2 इंटू में G इंटू में GTH माइनस में अल्फा इंटू में L इक्वल टू 1 अपॉन में नेचुरल लॉग ऑफ 1 अपॉन में R1 इंटू में R2. And to calculate the minimum threshold condition, that is GTH, will be equal to what? GTH will be equal to what? Alpha. Sorry. First of all, a natural log of 1 by 2 into में L natural log of 1 by R1 R2, and you will see that GTH, this is प्लस में माइनस अल्फा, GTH will be equal to अल्फा प्लस में 1 अपॉन में ट्वाइस ऑफ L natural log of 1 by R1 R2. So this is a threshold condition, that is GTH comes out to be the alpha plus में 1 upon में 2 into में L natural log of 1 by R1 into में R2. Clear? So next one is the laser diode rate equation. In the threshold condition, that is the minimum gain should be achieved by the photon when it overcomes the attenuation plus में 1 upon में 2 into में natural log of 1 by R1 out. Then only the laser oscillations will get sustained for the longer period of time. So next one is the next topic is the laser diode rate equation. In the laser diode rate, before we start with the laser diode rate equation, you should know that in the laser working, mainly is the stimulated emission will take place, that is main, and but side by side spontaneous emission will also take place, and that spontaneous emission is mainly at the initiation side, at the initiation. Clear? So laser diode rate equation can be described by the rate equations of for the electrons and the photon density in the active layer of the device. Means can be described by the rate equation for the electron and the photon density, means the rate of change of electron and the rate of change of the photon with respect to time. Now in the LED we can directly signifies that the graph is the linear, means the number of electron which is get changes and at the same rate photon gets generated. Okay? Means if I say n 100 electrons if I inject into the LED, and if I suppose to have a all radiative recombination, means that the photons will also generated, that is equal to 100 at the same rate. In the LED at the same rate electron get decayed, and at the same rate photon get generated in the LED. But in the case of laser, the rate at which electrons decays is not equal to the rate at which photon density get increased, because there is a stimulated emission, and in the stimulated emission you have observed that if one photon triggers the electron and that electrons moves through the conduction band, it releases two photons, and these two photons further excites the electron, then electron move to the conduction band, and when electron move to the conduction band, when it releases energy, the electron comes back to the valence band. It releases 4 photons. Means rate of generation of photon, that is equal to 1, 2, 2, 4, 4 creates 8, 8 creates 16, and this comes to the maximum. So in the stimulated emission we can say, or in the stimulated emission or in the laser, we can say the rate of change of electrons is not equal to the rate of change of the photon density, because the rate at which electron decays is not equal to the rate at which the photon density increase. Clear? So that's why there is a two rate of equation, that is the one for the electron density, rate of change of electron, and the rate of change of the photon density in the active layer of region. Now now see this one. This is the rate of change of electron with respect to time. The first equation, that is the rate of change of electron with respect to time, that is dN by dt, is equal to the electron which is supplied, number of electrons which is injected, minus में number of electrons decayed due to what? Due to spontaneous emission. In spontaneous emission minus में number of electrons decayed in stimulated emission. So we will see that dN by dt is equal to number of electrons injected, that is J by ED, minus में number of electrons decayed due to spontaneous emission, that is minus N by tau SP, minus में number of electrons decayed and stimulated, that is minus C into में N into में 5. Clear? Now see the rate of change of photon density. The rate of change of photon density, that is equal to generation of photons, due to stimulated emission, that is C into man into में 5. Clear? Plus में some photons generated due to spontaneous emission, when there is a radiative recombination. That's why it is equal to delta into में N by tau SP, because recombination rate. If I say all radiative recombination, that means delta comes out to be the 1. And some photons which is generated get lost or loss due to its photon lifetime. that is minus phi into my tau into my pH. Clear? So we'll see that the first term indicates that the increase in the electron concentration in the conduction band, that is the first term indicates the electron concentration in the conduction band as the current flows into in the junction diode, and the second term, this one n by tau sp and the cn phi, the electron loss from the conduction band by the spontaneous emission and the stimulated emission. Clear? In the second equation you will see that the first depict the stimulated emission as a source of photons, and second equation means the fraction of photons which is produced by the spontaneous emission. Clear? And the third is the, that is third term, this one is the final term, will represent a decay in the number of photons resulting from the losses in the optical cavity. It means some photons get decay in the due to the loss in the optical cavity. So the rate equations are described by two. Now if I want to say that the Loisel oscillation gets sustained, so we have to study about the steady state behavior of the semiconductor laser. Further, from the first equation, from the equation number 1, you will see that if I say this is equation number, if I say the steady state equation gets equaled up, means dn by dt is equal to 0, and ignore the spontaneous emission, because in the laser oscillations we have to mainly consider about the stimulated emission. So ignore the spontaneous emission, you will see that the Cn into my phi is comes out to be the J upon my Ed, and from equation number 2, so J by Ed is equal to C into my n phi, and from equation number 2, d phi by dt, from equation number 2 put d phi by dt is equal to, for the steady state equation, means when the production of photons get sustained, d phi by dt is equal to 0, you will observe that Cn into my n phi, C into my n phi, ignore the spontaneous emission, will become equal to minus phi into my tau pH, minus my phi into my tau pH is equal to 0. Clear? And for the laser oscillation for the steady state, this condition should be greater than equal to 0, which means that is equal to this mean. Clear? Ignore the spontaneous emission. For the steady state emission, in the stimulated emission, this should be equal to 0. You will see that Cn should be phi get cancelled out, that is equal to 1 upon my tau pH, and this n equal to 1 upon my C into my tau pH. Now put this equation as a equation number 3, and if n is larger than the, if I say for the steady state equation, the electron which is involved in the stimulated emission is greater than the threshold condition, then the photon generated will get, means minimum threshold condition, minimum electrons which is involved in the stimulated emission, that is NTH equal to 1 upon my C into my tau pH. Clear? Now see this NTH, can I say this NTH is related to the current density which is applied, means the threshold current which is applied can be related to the NTH will be equal to what? JTH. If I say minimum threshold condition, minimum threshold electrons which is applied at the in the laser device for the stimulated emission, that is NTH, means that the minimum current density which is applied in the laser for the stimulated emission, that is equal to threshold current density, at which n comes out to be NTH and phi equal to 0. Now see this one, equate this equation, this is equation number this you will see that this NTH equal to 1 upon में C into में tau pH. This is equation number 3, and let's say this is, and this will be equation number what? This is equation number 4, let's say. Clear? Now equate equation number 3 and 4, because when n equal to NTH at this equal at that time, threshold photons which is generated due to stimulated emission will be equal to what? 0 na. This will be equal to 0, because if I say minimum current which is applied for the stimulated emission, that is GTH, at that time the photons which is produced due to stimulated emission will be equal to what? Minimum, that is equal to 0. That means this term equal to 0, that is J by AD. Equate number 3 and 4. You will observe that JTH by AD equal to N upon में tau SP. Clear? And this is equal to JTH upon में AD equal to NTH upon में tau SP. So current required to sustain the excess electron density steady state condition, that is equal to phi equal to J by JTH upon में ED minus में C into NTH into में phi S, and for the steady state photon generation, that is 1 upon में C into में NTH equal to J minus में JTH upon में ED, and from the equation you putting the value of C into NTH from this from this you will see the equation, put the equation from the C NTH here. You will observe that put the value of this, that is phi S comes out to be tau pH upon में ED equal to minus J into में JTH. So the photon density cannot be a negative quantity, as this is meaning like then the phi S to be greater than equal to 0. The current must exceed its threshold value, and at that point J is the GTH. For the, if J is greater than GTH, then the stimulated emission will take place, and if J is less than threshold condition, means only spontaneous emission will take place. Means if I say the graph, that is equal to will be like this one. This is JTH and the current density applied. As the photon density, each photon has its energy, that is equal to GTH equal to beta into में JTH. Beta is the gain factor, is a constant that is appropriated to the specific device. That means minimum threshold condition for the current density will be equal to 1 upon beta alpha plus में twice of L equal to Ln into में R1 into में R2. Clear? So this is a laser diode equation which I have explained in the previous slide. Thank you for preparing these slides. I have referred the book, that is Optical Fiber Communication Principles Practice by the John M. Senior. Thank you.